Good morning, everyone. Welcome to today's presentation. I'm excited to have you here. Today, we'll be exploring topographical surveying, focusing on contouring, the characteristics and use of contours, and map reading. Over the next few slides, we'll cover these topics thoroughly. So let's get started and dive into the fascinating world of topographical surveys. Let's start by understanding what a contour actually is. Imagine drawing an imaginary line on the ground that connects all the points at the same elevation. So, a line that joins points sharing the same height above sea level. That's what we call a contour. In simpler terms, a contour is a line on a map where the ground surface intersects with a level surface, which is just a flat surface at a specific elevation. When we look at a map, this line, representing those points of equal elevation, is called a contour line. This concept is fundamental because it helps us visualize the shape and slope of the terrain without being physically there. It's a key part of contouring, which is all about mapping and understanding the elevation changes across a landscape. So, essentially, contour lines are our tools for reading the terrain's shape and getting a sense of how the land rises and falls. This understanding connects directly to our overall theme of terrain analysis and map reading. When we look at a general map of a country, it shows us the locations of roads, railways, rivers, villages, towns, and other features. But one thing it doesn't reveal is the nature of the ground surface itself. And that's a critical point. Because for engineering projects, whether we're planning roads, railways, or other infrastructure, we need to understand the terrain more deeply. We need to know about the ground surface to find the best alignments and to accurately estimate how much earthwork will be involved. That's where the contour map comes in. It's an essential tool because it provides detailed information about the elevation and shape of the land, which a general map simply can't show. That's why we prepare contour maps. They are vital for all engineering projects, ensuring we have the right understanding of the ground to plan effectively. Let's take a closer look at the contour map. A map that features contour lines is known as a contour map. These lines are crucial because they provide us with information about the altitudes of various surface features. Essentially, they show us how high or low different parts of the terrain are. What's really interesting is that a contour map serves a dual purpose. It not only gives us a plan view, showing the surface features from above, but it also acts like a sectional view, giving us an idea of the terrain's profile. This makes it a very versatile tool in fields such as surveying, geology, and civil engineering. Understanding contouring is key here. It's the process of drawing these contour lines which helps us interpret the landscape more effectively. So, in essence, contour maps are invaluable because they combine the plan and section perspectives, helping us visualize the terrain in a comprehensive way. All right, let's talk about contouring. Contouring is essentially the process of tracing contour lines on the surface of the Earth. These lines represent points of equal elevation, helping us understand the shape and slope of the terrain. When we draw these lines, we're creating a map that visually communicates the land's elevation changes. This is a fundamental concept in fields like topography, cartography, and geology. By understanding and using contour lines, we can better analyze landforms, plan construction projects, or even navigate through unfamiliar terrain. So, contouring is really about translating the three-dimensional surface of the Earth onto a two-dimensional map, making complex land features easier to interpret and work with. Let's talk about the purpose of contouring. Contour survey is typically conducted at the beginning of any engineering project, whether it's a road, railway, canal, dam, or building. Its main goal is to gather essential information about the land's shape and elevation. One key purpose is to prepare contour maps, which help us select the most economical or suitable site for the project. By understanding the terrain, we can avoid unnecessary costs and challenges. Another important reason is to determine the best alignment for canals. Ideally, a canal should follow a ridgeline to minimize water loss and construction effort. Similarly, when planning roads and railways, contouring helps us mark their alignment in a way that reduces the amount of earthwork needed. This means less cutting and filling, which can significantly cut costs and save time. Overall, contour surveying provides the critical data needed to design efficient, cost-effective projects by understanding the land's natural features. It's a foundational step that influences the success and sustainability of our engineering work. Now, let's look at some additional important purposes of contouring. First, it helps us gather information about the ground's nature, whether it's flat, undulating, or mountainous. This is crucial because it influences how we plan and execute projects. Next, contouring allows us to determine the capacity of a reservoir and the volume of earthwork needed, especially in mountainous regions where the terrain is more complex. This helps us estimate resources accurately and plan effectively. Another key point is that contouring helps us trace out the given grade of a particular route. This ensures that roads and pathways follow the desired slope, making transportation safer and more efficient. Finally, contouring is essential for locating physical features on the ground, like ponds, depressions, hills, steep slopes, or small slopes. Recognizing these features allows us to make informed decisions about construction, drainage, and land use planning. All of these points emphasize how contouring provides vital information for various engineering and planning tasks, making it a fundamental tool in our work. Let's talk about contour intervals. The contour interval is the constant vertical distance between two consecutive contours. Think of it as the uniform step in elevation from one contour line to the next. It helps us understand the elevation change over a landscape in a consistent way. Now, moving on to the horizontal equivalent. This is the horizontal distance between any two adjacent contours. Unlike the vertical difference, this horizontal distance can vary depending on how steep or gentle the slope is. It's important to remember that while the contour interval remains constant between contours, the horizontal equivalent is variable. If the ground is steep, the horizontal distance between contours will be small, but on gentle slopes, it will be larger. Understanding these concepts is essential because they give us a clearer picture of the terrain's shape, how elevation changes across the landscape, and how that relates to the ground's slope. This forms the foundation of contouring, which is a key skill in map reading and land assessment. Now, let's look at the factors on which the contour interval depends. The key idea here is that the contour interval is not fixed. It varies based on certain ground characteristics. The first important factor is the nature of the ground itself. For example, in flat and uniformly sloping areas, the contour interval can be quite small because the elevation changes gradually. This allows us to capture subtle variations in the terrain. On the other hand, in broken or mountainous regions, the terrain is much more rugged, and if we used a small contour interval, the contours would come too close together, making the map cluttered and difficult to read. In such cases, a larger contour interval is preferable to keep the map clear and readable. So, understanding the terrain's nature helps us decide the appropriate spacing between contours, which is essential for accurate and effective contouring. Now, let's talk about the factors on which the contour interval depends. One of the key factors is the purpose and extent of the survey. Basically, if you're surveying a small area and the maps are intended for detailed design work or to estimate earthwork quantities, you'll need a smaller contour interval. This allows for more detailed and accurate representations of the terrain. On the other hand, if you're dealing with a large area and the survey is for less detailed purposes, like general planning or overview maps, a wider contour interval is more appropriate. This helps keep the map simpler and easier to interpret without unnecessary detail. So, in summary, the contour interval is adjusted based on whether you need precision for small, detailed projects or a broader overview for larger, less detailed tasks. This ensures that the map serves its intended purpose effectively while being as clear and useful as possible. Now, let's look at the factors that influence the choice of contour interval. First, the scale of the map plays a crucial role. Essentially, the smaller the scale, meaning a less detailed map, the larger the contour interval should be. This makes sense because on a small-scale map, features are generalized, so we don't need very fine elevation differences. Conversely, on larger-scale maps, we can afford to have smaller contour intervals to show more detailed elevation changes. Next, we need to consider the time and expense involved in both field and office work. If we choose a smaller contour interval, it means more detailed data collection in the field, more survey points, and more plotting work in the office. This increases the time and cost of the entire process. So, it's a balance. While smaller intervals give more detail, they also require more effort and resources. Overall, selecting the right contour interval is about finding that balance between the necessary level of detail and the practical constraints of time and budget. This ensures our maps are both accurate and efficient to produce. Let's talk about the common values of the contour interval that are used for different purposes. When working with large-scale maps of flat areas, or for building sites, detailed design work, or calculating earthwork quantities, the contour interval typically ranges from 0.2 to 0.5 meters. This smaller interval allows for more precision and detail, which is crucial in these cases. By choosing an appropriate contour interval, we can ensure that the maps or plans accurately represent the terrain and support effective decision-making. This detail is especially important in projects where accuracy directly impacts costs and outcomes. So, understanding these standard values helps us select the right contour interval for each specific task, ensuring clarity and precision in our work. When it comes to the common values of the contour interval, there are different standards depending on the purpose of the map or survey. For reservoirs and town planning schemes, the contour interval typically ranges from about 0.5 meter up to 2 meters. This finer scale helps in detailed planning and ensures accuracy for construction and infrastructure. For location surveys, which require a slightly broader view but still need reasonable detail, a contour interval of around 2 to 3 meters is common. This balances detail with efficiency, allowing surveyors to accurately capture the terrain without excessive work. When dealing with small-scale maps, especially of broken country or areas where general topography is sufficient, the contour interval can be much larger, ranging from 3 meters up to 25 meters. These larger intervals help simplify complex terrain and make the maps more readable at a glance. Overall, choosing the right contour interval is crucial because it directly influences how well the map communicates the terrain's features, whether for detailed engineering work or broader geographic overview. Let's take a closer look at the characteristics of contours. All points along a single contour line share the same elevation, which helps us understand the shape of the land. When the ground is flat, you'll notice the contours are spaced far apart, indicating a gentle or flat surface. Conversely, on steep slopes, the contours are closely packed together, showing a rapid change in elevation over a short distance. A uniform slope is represented when the contour lines are evenly spaced, illustrating a consistent incline. And when you see straight, parallel, and equally spaced contours, that indicates a plane surface, meaning the surface is perfectly flat and even. Understanding these characteristics is fundamental because it allows us to interpret terrain features accurately from contour maps, connecting to the overall theme of terrain analysis and landform interpretation. Let's take a closer look at the characteristics of contours. When you see a series of closed contour lines on a map, they can tell us a lot about the terrain. Specifically, if the higher values are located inside those lines, it indicates the presence of a hill. Essentially, the contours form a concentric pattern that rises towards the center. So, those enclosed lines with increasing elevation as you move inward help us identify the hill's location and height. This concept is fundamental in understanding how to interpret topographic maps, as it allows us to visualize the landscape's elevation changes simply by analyzing the contour lines. Remember, this idea of contouring is crucial for accurately representing terrain features across various applications. Let's take a closer look at the characteristics of contours, specifically when it comes to depressions. When you see a series of closed contour lines on a map, it usually indicates a specific feature. Now, if the higher values are outside these closed lines, that suggests the area inside is actually a depression. Think of it like a bowl or a sinkhole. The elevation decreases towards the center, and the contours form a closed loop that encloses a lower area. This is important because it helps us identify depressions on the map. In the examples shown here, notice how the numbers on the contour lines are decreasing as you move inward. That's a key indicator that you're looking at a depression. The lines form a closed shape, and the higher numbers are on the outside, which confirms the depression's location. Understanding these characteristics is crucial for accurately interpreting topographic maps, especially in fields like geology, hydrology, and environmental planning. Recognizing depressions can help us assess water flow, erosion patterns, or even potential flood zones. So always remember, when contour lines form a closed loop with higher values outside and lower values inside, you're looking at a depression. This concept ties into the broader theme of how we read and interpret the terrain using contour maps. Let's take a closer look at the characteristics of contours, starting with the ridgeline. As you can see from the diagram, the elevation values are marked along the contour lines, ranging from 50 up to 100. These numbers help us understand the height at each contour, and they are crucial for interpreting the terrain's shape. Now, when we talk about a ridgeline, we're referring to the highest points along a crest, the ridges that stand out in the landscape. Contour lines that form a ridge typically run along the crest, and they tend to be closely spaced, indicating a steep slope. This brings us to the concept of contouring. Contouring is the process of drawing these lines to represent elevation changes on a map. It's a fundamental technique in topography because it visually communicates the terrain's form, whether it's a gentle slope or a sharp cliff. Understanding how contours behave around features like ridges helps us interpret landforms more effectively. For example, closely spaced contours indicate steep terrain, while wider spacing suggests gentler slopes. So, in essence, contours and ridge lines are key to decoding the landscape, helping us visualize the terrain in a way that's both precise and intuitive. Let's take a closer look at the characteristics of contours, starting with the valley line. As you can see, the elevation values range from 100 down to 50. These numbers help us understand the terrain's height at different points. Contouring, or contouring, is the process of drawing lines that connect points of equal elevation, which is fundamental for visualizing the shape of the land. The valley line, in particular, indicates the low points in the terrain, areas where water might naturally flow or collect. Recognizing these features is crucial for various applications, from planning construction projects to understanding natural water systems. So, in essence, contours and valley lines give us a detailed picture of the terrain's characteristics, helping us interpret the landscape more effectively. Contours cannot end just anywhere on a map. Instead, they must always close on themselves, either within the map boundaries or outside of them. This is a fundamental characteristic of contour lines. It helps us understand that contours are continuous and represent a consistent surface. If a contour line appears to end abruptly in the middle of the map, it usually indicates an error or an incomplete data set. Remember, the key idea here is that contours form closed loops. They never just stop in the middle of our map. Whether they are inside the area we're studying or extend beyond the limits, they will always close on themselves. This concept is crucial because it ensures the integrity of our topographic or thematic representation. It allows us to interpret elevation, slope, or other data accurately, knowing that these lines are reliable and complete. So, whenever you're analyzing contours, always check for these closed-loop patterns to confirm the data's consistency and correctness. Now, let's talk about contour lines and their behavior on maps. One key point to remember is that contour lines cannot cross or merge with each other under normal circumstances. This is important because it helps us understand the terrain without confusion. However, there is an exception to this rule: overhanging cliffs. In such cases, the contours can appear to overhang or dip back over themselves, which might look like crossing lines, but it's actually a special case. So, to sum up, contour lines are designed to never intersect, ensuring a clear representation of elevation. But overhanging cliffs are a unique feature where the typical rule is momentarily bent, allowing the lines to behave differently. This understanding is crucial as we interpret topographic maps accurately and confidently. Let's talk about the behavior of contour lines. Usually, contour lines never run into each other. That's because each line represents a specific elevation, and in a normal landscape, they stay distinct and separate. However, there's an important exception to keep in mind when you have a vertical cliff. In that case, multiple contours can actually coincide or overlap. This happens because at a vertical cliff, the elevation changes very suddenly, almost instantaneously, so the horizontal difference, what we call the horizontal equivalent, becomes zero. It's like the contours are stacking or merging together because the terrain is vertical. So, understanding this behavior is crucial because it helps us interpret the landscape correctly, especially when we see overlapping contours or very close lines indicating steep or vertical features. Recognizing this exception allows us to better analyze and visualize complex terrains. Now, let's talk about a key characteristic of contours: the saddle. A saddle is essentially a depression that exists between summits, and you can think of it as a kind of dip or notch in the landscape. It's usually represented by 4 sets of contours, which you can see in the diagram. This feature often appears where 2 ridges meet or at a junction point. In the case of a mountain range, a saddle typically forms what we call a pass, a sort of natural route through the mountains. When we look at the contour lines passing through these saddles and summits, they form what is known as a watershed line. This line is crucial because it indicates the boundary that separates water flow into different drainage basins. So, understanding the saddle and watershed lines helps us grasp how water moves across the terrain, which is fundamental in topographical mapping and planning. Overall, recognizing these features helps us interpret the landscape more accurately and understand how natural formations influence water flow and terrain navigation. Let's talk about the methods of contouring. There are mainly 2 ways to locate contours: the direct method and the indirect method. Starting with the direct method, this approach involves physically going out into the field and directly tracing the contours. Essentially, you identify and mark a series of points along each contour line right on the ground. Once these points are marked, they are surveyed to determine their exact positions. After that, these points are plotted on a plan or map, and then you draw the contour lines through these plotted points. This method is quite straightforward because it involves direct measurement and marking, making it very accurate for detailed surveys. However, it can also be time-consuming, especially over large areas. In summary, the direct method of contouring relies on physically marking points on the ground and then connecting them on the map to form the contour lines. This technique is fundamental in topographic surveying and helps us accurately understand the terrain's shape. Now, let's talk about the direct method of contouring. This method is considered the most accurate because it involves precisely identifying points of the same elevation across the area. However, it's also quite slow and tedious since a lot of time is spent searching for those specific points. Due to this, it's best suited for small areas where high accuracy is essential. When accuracy is critical and the area is manageable, this method ensures the contours are as precise as possible. Keep in mind, though, that for larger areas, this approach can become impractical because of the significant amount of time it requires. So, understanding when and where to use this method is key in our overall contouring process. Let's walk through the procedure step by step. First, we establish a temporary benchmark, or BM, near the area we want to survey. This is done in reference to a permanent BM using fly leveling techniques. The purpose here is to create a stable reference point close to our survey site. Next, we set up the level instrument in a position that allows us to command as many points as possible from that single station. The idea is to maximize efficiency and accuracy in our measurements. To determine the height of the instrument, we take a back sight reading on the temporary BM and add this reading to the known reduced level, or RL, of the benchmark. This gives us the exact height of the instrument above a fixed point. Finally, to fix points on various contours, we calculate the staff readings by subtracting the RL of each contour from the height of the instrument. This process helps us accurately determine the elevation at different points across the surveyed area, which is essential for creating precise contour maps. Let's consider an example to understand this better. Suppose the height of the instrument is set at 82.48 meters. In this case, the staff readings needed to locate the 82, 81, and 80-meter contours would be 0.48, 1.48, and 2.48 meters respectively. What this means is, we hold the staff at an approximate position of the point we're measuring, then carefully move it up and down along the slope. The goal is to find the exact spot where the staff reading matches the desired contour height. Once we find this point, we mark it with a peg. This process helps us accurately trace out the contours on the landscape, which is essential for mapping and surveying tasks. Understanding this method is key to effective contouring, as it ensures precision when recording the elevation lines across the terrain. Now, continuing with the concept of contouring, it's important to understand that various points are marked on each contour line. When we connect all these points, they form the actual contour line. Think of it as drawing a line that follows the shape of the terrain or surface we're studying. An important thing to note here is that only one contour is set at a time, which helps us accurately map specific elevations or features. Once we fix the contours within the instrument's range, we then shift the level and set it up in a new position to continue the process. This method allows us to build a detailed and precise representation of the surface, which is essential for accurate surveying or mapping work. Essentially, the key idea is that by carefully marking points and connecting them, we create a reliable contour map that reflects the terrain's true shape. Now, after we have our initial measurements, the new height of the instrument and the required staff readings are then calculated in a similar manner. This process is repeated systematically until all the contours are accurately located across the terrain. The positions of these contour points are determined either simultaneously with leveling or sometimes afterwards, depending on the specific method used. Typically, to locate these points, we use instruments such as a theodolite, a compass, or a plane table traversing. These tools help us precisely establish the position of each contour point on the ground. Once we've marked these points, the next step is to plot them accurately on our plan. From there, drawing the contours involves joining these points with dotted, curved lines. These lines represent the terrain's shape and elevation changes, giving us a clear visual of the land's surface. This entire process is essential for creating an accurate topographical map, which in turn informs various engineering, construction, and planning activities. This method is particularly suitable for small areas, where a single point in the center can effectively oversee the entire region. To implement it, we lay out radial lines from this common center point using a theodolite or a compass. The key here is that once these lines are established, their positions are fixed by measuring horizontal angles and bearings. This allows us to accurately map the contours within the small area. The diagram on the slide illustrates how these radial lines extend outward, creating a network that we can use to determine elevation changes and contour lines. This approach simplifies the process for small-scale surveying, making it efficient and precise. It's especially useful when the area is compact enough that a central point can command the whole survey zone, ensuring we capture the necessary topographical details effectively. Let's move on to the next part of the direct method using radial lines. First, we establish temporary benchmarks at the center and near the ends of these radial lines. These benchmarks serve as reference points to help us accurately locate the contour points. Once the benchmarks are in place, we identify and mark the contour points along these lines. To do this, we measure their distances from the benchmarks along each radial line. This way, we determine the exact positions of the contour points in relation to our reference points. After measuring, we plot these points on our plan. And with the help of a plane table instrument, we join all the corresponding points to draw the contours. This method is quite effective because it allows us to accurately transfer the elevation data from the ground to our plan, ensuring a precise representation of the terrain. It's a systematic approach that combines measurements and plotting for reliable contour mapping. Now let's take a closer look at the indirect method of contouring. In this approach, the points we survey are not necessarily exactly on the contour lines themselves. Instead, we take spot levels at various points across the area. These points are chosen based on their significance, like hills, depressions, ridges, and valleys, to represent the terrain accurately. We then plot these spot levels on the plan, connecting them through interpolation to draw the contour lines. This method is often called contouring by spot levels because we're essentially estimating the contours based on the surveyed points rather than directly following the lines. It's a practical approach, especially when direct contouring isn't feasible, and it helps us understand the terrain's slope changes across the entire area. This method is valuable because it provides a detailed and accurate representation of the landscape by analyzing key points, making it a crucial technique in our surveying toolkit. Now, let's take a closer look at the contouring square method. This technique is a practical approach for creating smooth, natural-looking contours in various design applications. Essentially, it involves breaking down complex shapes into a series of squares, which makes the process more manageable and precise. The key idea here is that by focusing on these squares, we can better control the flow and direction of the contour lines, ensuring they follow the form accurately. This method is especially useful when working with organic shapes or when trying to achieve a more realistic, three-dimensional effect. Overall, the contouring square method is a valuable tool in our toolkit because it promotes consistency and clarity in how we develop contours, tying back to our broader theme of mastering effective design techniques. This method is commonly employed in all kinds of surveys because it is cheaper, quicker, and less tedious compared to the direct method. When we talk about the main ways of contouring in the indirect method, there are primarily three. The first one is by squares. In this approach, we divide the entire area into a number of squares. The size of these squares can vary, typically ranging from 5 meters to 30 meters, depending on the nature of the ground and the desired contour interval. It's important to note that the squares do not have to be of the same size throughout the entire area. This flexibility allows us to adapt the grid to the terrain, making the surveying process more efficient. Essentially, this method simplifies the process of contouring by breaking down complex terrain into manageable, measurable sections. Now, let's look at how the corners of the squares are pegged out and how we determine the reduced levels of these points using a level. This is the fundamental step in ensuring accurate measurements in our survey. Moving on to the indirect method, specifically the square method, you can see the diagram and the table on the slide. The squares laid on the ground are numbered from 1 to 16, and the corresponding reduced levels for each point are listed. These levels are obtained by measuring from known reference points or benchmarks. Notice the table showing the reduced levels at each corner. For example, point 1 has a level of 100.4, point 2 is at 97.6, and so on across the grid. These values are critical because they serve as the basis for contouring and mapping the terrain. The next step involves interpolating the contours, which are shown here as the contour lines at intervals of 32 units. Contouring helps us visualize the shape and elevation changes of the land surface based on these measured points. Finally, the process of contouring, as depicted on the slide, involves connecting points of equal elevation to create a contour map. This map provides a clear representation of the terrain, essential for planning and analysis. In essence, this method allows us to accurately determine and represent the surface elevation by systematically measuring, interpolating, and contouring the data points. Let's take a closer look at the indirect method, also known as the square method. On this slide, you can see a set of numbers arranged in a grid. These numbers represent the reduced levels at various points within the squares. The key idea here is that we don't always measure directly to every point we need. Instead, we use the measurements from the corners of these squares to find the important points within them. By doing so, we can efficiently determine the elevation or reduced level at any point inside the square. The process involves plotting these squares on the plan and writing the reduced levels of the corners. From these corners, measurements are taken to locate the points of interest, usually the highest or lowest points, or those critical for contouring. This method is particularly useful because it simplifies the process of mapping and leveling over complex terrains, especially when combined with contouring techniques. It allows us to accurately determine the topography by focusing on key points within each square, saving time and effort. So, the main takeaway here is that the square method is a systematic approach to contouring and leveling, relying on measurements from square corners to locate important points, which are then plotted to help us understand the terrain better. Now, let's look at the indirect method, specifically by cross-sections. This approach is particularly useful when surveying long, narrow strips like roads, railways, or canals. You can see in the example how the readings are taken at different points along the cross-sections, which helps us determine the depression or the variation in terrain. Notice the elevations recorded at various stations, with the readings such as 70.6, 69.1, 68.8, and so on. These values are crucial because they help us analyze the land profile. The difference between the high and low points indicates the depression or the slope of the terrain. The diagram, labeled as Fig. X-section method, visually represents these cross-sections and the depression levels, like RD 580, RD 560, RD 540, and RD 520. These reference points give us a clear picture of the land's shape along the survey line. This method essentially allows us to interpolate the terrain features between the cross-sections by analyzing the recorded data. It's a practical approach for long, narrow strips where direct measurement might be less feasible or too time-consuming. In summary, the cross-section method provides a systematic way to understand terrain variations over lengthy, narrow strips, which is vital for accurate planning and construction. Let's now look at the indirect method, specifically using cross-sections. This approach is especially useful when surveying long, narrow strips like roads, railways, or canals. Essentially, we run cross-sections perpendicular to the center line of the work, and these lines help us gather representative points along the strip. It's important to note that these cross-section lines don't always have to be at right angles. They can be inclined at any angle to the center line if needed, depending on the terrain or other considerations. The spacing between these cross-sections isn't fixed and largely depends on the topography of the area and the specific requirements of the survey. The key is to choose a spacing that captures the variations in the terrain accurately without being unnecessarily detailed. This method allows us to effectively analyze and map the surface features over long, narrow areas by breaking them into manageable, measurable sections. Now, let's look at how the common value varies depending on the terrain. In hilly country, the typical difference in elevation between points is around 20 to 30 meters. In contrast, in flat country, this value can be as much as 100 meters. When we plot the levels of these points along our section lines on the plan, we then interpolate the contours in the usual way, as shown in the figure. This process helps us visualize the terrain more clearly. Moving on to the indirect method, specifically when we're using cross-sections, this approach allows us to generate contours without measuring every single point directly on the ground. By taking cross-sections at regular intervals, we can record the levels at key points along each section. Then, by connecting these points, we interpolate the contours across the area. This method is especially useful in difficult terrains or large projects, where direct contouring might be impractical or too time-consuming. So overall, whether we're working with hilly or flat terrain, understanding how to interpolate contours from section lines is a crucial part of accurate land surveying and mapping. Now, let's move on to the second method under the indirect method, which is the tachyometric method. A tachyometer, as you can see, is a special type of transit theodolite. It has a diaphragm fitted with two stadia wires, one positioned above the central wire and the other below it. The key idea here is that the horizontal distance between the instrument and the staff station can be determined quite efficiently. We do this by measuring the difference in staff readings between the upper and lower stadia wires. Then, we multiply that difference by the stadia constant of the instrument, which is typically 100. This allows us to calculate the horizontal distance directly. What's really useful about the tachyometric method is that it helps us measure both vertical and horizontal distances, making it versatile for various surveying tasks. As shown in the figure, the stadia wires at the diaphragm are essential for these measurements. So, in essence, the tachyometric method is a practical way to quickly and accurately determine distances without needing to measure them directly. Now, let's focus on the tachyometric method, which is a specific approach within the indirect method. This technique is especially useful in hilly areas. Why? Because the number of stations that a tachyometer can command is much greater than those accessible by a level, which means we can cover more ground with fewer instrument setups. Here's how it works. We lay out several radial lines at known angular intervals, much like spokes on a wheel. Along these radial lines, we mark points with pegs, which serve as our reference points. Using the tachyometer, we measure the elevations and distances to these points. Once we've gathered these measurements, we plot the points on our plan. From there, we interpolate the contour lines, creating a detailed representation of the terrain. This method is efficient and particularly suited for rugged, hilly terrains, making our surveying more effective and less time-consuming. It's a great example of how choosing the right method can simplify complex terrains and improve accuracy. Let's talk about the interpolation of contours. This process involves spacing the contours proportionally between the plotted ground points. Essentially, when we're doing indirect contouring and only have spot levels, we need a way to estimate the contours in between. That's where interpolation comes in. It helps us create a smooth, continuous representation of the terrain. During interpolation, we assume that the ground between any 2 points is uniformly sloping. This assumption simplifies the calculations and allows us to estimate the position of the contours accurately. By doing this, we ensure that the contours are evenly spaced and proportionate, which is crucial for accurate mapping and analysis. This step is important because it bridges the gap when direct measurements aren't available for every point, making our maps more precise and useful. It's a key part of the contouring process, helping us visualize the terrain effectively, even with incomplete data. Now let's look at the interpolation of contours. There are 3 main methods used for this process, and I'll walk you through each of them. First, we have the method called by estimation. Essentially, in this approach, we estimate the position of the contour points between ground points. These ground points are the known data points, and we roughly guess where the contours should pass through between them. Once we've made these estimations, we draw the contours through these estimated points. This method is quite simple and quick, making it suitable mainly for small-scale maps where detailed accuracy isn't as critical. Moving on to the second method, which is by arithmetical calculation. This one is a bit more involved, but offers higher accuracy. It involves detailed calculations to interpolate the contour lines precisely. Although it can be tedious, meaning it requires more time and effort, it is very reliable. This method is especially used for small areas where obtaining accurate results is essential. The process involves using mathematical formulas to interpolate the values between known points, ensuring the contours reflect the true variations in the terrain or data. Connecting this to the overall theme of contouring, understanding these methods helps us choose the right approach based on the map's scale, required accuracy, and the available data. Whether we opt for estimation or precise calculation, each method plays a vital role in producing meaningful and useful contour maps. Let's talk about the interpolation of contours. Suppose we have 2 points, A and B, which are 30 meters apart. The reduced level of point A is 25.45 meters, and for point B, it's 27.54 meters. Since our contour interval is 1 meter, we can interpolate the 26 and 27 meter contours between these 2 points. Now, the difference in level between A and B is 2.09 meters. The difference in level between point A and the 26-meter contour is 0.55 meters, and between A and the 27-meter contour, it's 1.55 meters. To find the horizontal distance from point A to each of these contours, we use the ratio of the level difference to the total difference, multiplied by the distance between A and B. So, the distance from A to the 26-meter contour is 0.55 divided by 2.09 times 30 meters. Similarly, the distance from A to the 27-meter contour is 1.55 divided by 2.09 times 30 meters. Once we have these distances, we plot them to scale on the map, which helps us accurately represent the terrain's contours. This method, whether by proportional calculation or arithmetical calculation, allows us to interpolate contour lines precisely between known points, making our topographical maps much more detailed and useful. Let's talk about the interpolation of contours using graphical methods. This approach is actually simpler than the arithmetical method, and what's great is that the results tend to be quite accurate. Among the various graphical techniques available, the most commonly used one is the method we'll focus on today. Imagine you have 2 points, labeled A and B, with known elevations. Say 51.5 meters at point A and 62.5 meters at point B. By plotting these points on a graph and connecting them, you can interpolate the elevation at any intermediate point along that line. For example, if you look at the points marked 50, 55, 60, and 65 meters on the graph, you can visually estimate the elevation at any specific location between A and B. This method allows us to draw contours more intuitively, especially when dealing with complex terrains. So, in essence, the graphical method simplifies the process of contour interpolation by relying on visual estimation rather than complex calculations. It's a practical tool that helps us accurately represent elevation changes, which is crucial for effective contouring in surveying and mapping projects. As shown in the figure, let's assume the contour interval is 5 meters. Now, on a piece of tracing cloth, we draw a series of parallel lines spaced at 0.5 meters, which is usually 1/10 of the contour interval. Every 10th line is made thicker to help us easily identify the major contour lines. Suppose we need to interpolate contours between 2 points, A and B, where the elevations are 51.5 meters and 62.5 meters, respectively. The graphical method involves plotting these points and then drawing the intermediate contours by estimating where they would fall between A and B, based on their elevations. This process helps us understand the terrain more precisely, especially when the exact contour lines are not available, and it forms a key part of our overall contouring technique. By connecting these concepts, we can accurately represent the elevation changes on the map, which is essential for various engineering and planning purposes. Now, let's look at the graphical method of contour interpolation. Suppose the bottom line on your map represents an elevation of 50 meters. The successive thick lines above it then represent higher elevations, such as 55 meters, 60 meters, and 65 meters, and so on. To find the points on these contours, we use a tracing cloth. First, place the tracing cloth so that point aligns up on the third line from the bottom, which corresponds to a specific elevation. Then, move the tracing cloth until point B aligns on the fifth line above the 60-meter thick line. When you do this, you'll notice where the thick lines, one representing 55 meters and the other 60 meters, intersect with the line ob. These intersections give us the approximate positions of the points on the 55-meter and 60-meter contours. We mark these points on the plan with a pin. This method visually helps us interpolate between known contours, making it easier to accurately plot elevation lines on our maps. Remember, this graphical approach is very useful because it simplifies the process of finding intermediate contours without complex calculations. It's a practical technique that ties into our overall theme of effective contouring and terrain modeling. Now, let's talk about drawing the contour lines. Contour lines are typically drawn as fine, smooth, freehand curved lines that follow the natural shape of the terrain. Sometimes, these lines are represented by broken lines, especially in areas where the elevation changes are less certain or to indicate features like ridges or valleys. When inking the lines, you can use either black or brown ink, but a drawing pen generally gives a cleaner, more precise line compared to a regular writing pen. Using French curves is highly recommended because they help create smooth, consistent curves that follow the terrain's natural flow. An important detail is that every fifth contour line should be made thicker than the others. This helps in easily identifying the elevation intervals and makes reading the map much simpler. When writing the elevation of these contours, it's best to do so consistently, either on the higher side of the line or within a gap left in the line itself. For very long contours, it's helpful to write the elevation at 2 or 3 different points along the line, so the reader doesn't have to trace the entire length to understand the elevation. And in small-scale maps, where detail might be limited, writing every fifth contour line's elevation is usually sufficient. This process of drawing and labeling contour lines is essential because it visually represents the terrain's shape and elevation, which is fundamental to understanding the landscape in any topographical map. Now let's look at the various uses of a contour map. A contour map provides valuable information about the features of the ground, whether it's flat, undulating, or mountainous. This makes it a crucial tool in understanding the terrain comprehensively. From a contour map, you can easily draw sections in any direction, which helps in planning and analysis. It also allows you to determine intervisibility between 2 ground points, meaning you can see if 2 locations are visible from each other, which is vital in many engineering projects. Speaking of projects, an engineer can use a contour map to select the most economical or suitable site for things like roads, railways, canals, or pipelines. It helps in tracing routes of a specific grade, ensuring the design is practical and efficient. Another important application is in determining the catchment area and capacity of a reservoir, which is essential for water resource management. Additionally, contour maps assist in calculating the quantities of earthwork needed for construction, making planning more precise. In essence, contour maps are versatile tools that support a wide range of engineering and planning activities by providing detailed terrain information.